we're talking about the case with the decomposition of sodium bicarb is that the delta H for that reaction and the delta S, they both had the same sign. And something that you can keep in mind in general is any time that both delta H and delta S have the same sign, it's actually possible to switch from spontaneous to non-spontaneous or vice versa just by changing the temperature of the reaction. And we can think about this graphically if we assume that delta H and delta S are independent of temperature, which is a good assumption to a first approximation. In this case, we find that the delta G of the reaction is the linear function of the temperature. So that means we can go ahead and graph what we saw for the case of baking soda. So our first point here was that we saw at room temperature, about 298 K, the delta G was positive. It was 36 kilojoules per mole. We also saw that once we heated it up to baking temperature, we actually had the delta G now at negative 15 kilojoules per mole. So since this is linear, we can actually draw a straight line right through here, and we can think about the fact that we have this temperature here where anything below this temperature has a positive delta G, and anything above this temperature is going to have a negative delta G. And let's actually think about the fact that this is a line and see what our slope and our y-intercept is going to mean. We can say that delta G is equal to negative delta ST plus delta H if we want to put it in the formation of the equation for a line. So what this tells us is that our slope is going to be negative delta S here. And if we think about our y-intercept, that's going to be the change in enthalpy for the reaction. So again, what I want to point out is that any time we're at a temperature that's lower than this change in temperature here, we're going to find that delta G is greater than 0, and we're going to be dealing with a non-spontaneous reaction. However, if we move our temperature up and up and up, so we go across the graph this way, eventually we'll hit a point where if we're above that temperature, we'll find that delta G is less than 0, and now we have a spontaneous reaction. So we can actually think about what this temperature is. We can call this T star. This is the temperature at which our reaction switches, whether it's spontaneous or non-spontaneous. And if you're thinking about trying to get a reaction to go, it's very important to be able to calculate what this temperature is. A lot of times in organic chemistry laboratories, they need to heat up reactions. Part of why they do that is kinetics, but the other part is sometimes they need to make a reaction go from being non-spontaneous to spontaneous. So let's think about how to calculate T star, or this change in temperature. So we're talking about this threshold temperature. So we're talking about where delta G is going to be equal to 0. Because if we set delta G equal to 0, we know that anything on one side of that temperature is going to be spontaneous, and the other side is going to be non-spontaneous. So if we do this, we can just rewrite our reaction. Delta G equals delta H minus T delta S. And let's plug in our 0 for delta G there, and now rearrange our reaction so that we're talking about this threshold temperature. So that T star is just going to be equal to the change in enthalpy divided by the change in entropy. So it's very easy for us to calculate. So let's go ahead and do this for the case with baking soda. And for baking soda, what we saw was that delta H was 136 kilojoules per mole. And the change in entropy was 0.334 kilojoules per K mole. And that means if we do that simple division, then what we end up with as our temperature star is 406 Kelvin. So basically what this tells us is if we tried to bake our cookies below 406 Kelvin, they would not rise. If we bake them above 406 Kelvin, they will rise because this reaction is now spontaneous.